Section 15.3 in your book is acid-base reactions. First idea we need to know about acid-base reactions is that acids dissociate in water. And so here's an example. We have acetic acid, as you can see there. If we look back at the previous section, at our acid-base theories, acetic acid is acting as an acid because its hydrogen ion is donating itself to water. So it's donating a hydrogen ion to water. That makes it an acid. It's hydrogen ion. Again, hydrogen ion really, what a hydrogen ion is hydrogen with an electron removed. So a hydrogen ion really is the same thing as a proton. So you might hear me say hydrogen ion. You might hear me say donate a proton. It is the same thing in this instance. A hydrogen without its electron is really just a proton. That's all that's left. Okay, so it's acting as an acid, donating a hydrogen ion. Water is accepting that hydrogen ion, so it is our base in this instance. So very interesting that water can act as a base. The other idea we want to get from this diagram is, well, a few things, is that if our acetic acid is an acid, once it loses its hydrogen ion, then it has a base. It can act as a base on the other side. So this is what we would call its conjugate base. So this is an acid-base conjugate pair. The acid is acetic acid. Acetic acid without its hydrogen ion can act as a base, so it's its conjugate base. Same thing for water in this instance. Water here is accepting the hydrogen ion, so it is a base, but once it accepts that hydrogen ion, it becomes hydronium. Hydronium, again, is the concentration we're looking at when we talk about acids. This is water's conjugate acid. So in this case, if water's acting as a base, this is water's conjugate acid. And you'll hear us talking about water acting as a base, acting as an acid a lot, because water has a property called amphoteric. We'll talk about that more, meaning it can act as an acid or a base. Let's look at this in a bit more detail. Here's a diagram of the same thing. I really like this diagram. Notice we have that hydrogen being donated to water. That makes this our acid, water our base. Notice on the other side, we have the conjugate base of acetic acid, which is our ion acetate, essentially, with a negative charge there because it lost its hydrogen ion, and water with that extra hydrogen, making it hydronium. So nice, kind of a nice visual of what is going on here to give us an acid, something that's donating a hydrogen, and a base, something that's accepting that hydrogen ion or proton. Let's look at other examples of conjugate pairs. So here we have acetic acid, which we know is a very strong acid. Well, acetic acid, we're talking about hydrochloric acid now, again, is donating its hydrogen ion to water. That makes water act as a base. It is the acid because it's donating the hydrogen ion. The conjugate base of hydrochloric acid is just the chloride ion. The conjugate acid, so our conjugate of water, again, after it accepts that hydrogen ion, is the hydronium ion. Again, hydronium is the name of water with a hydrogen ion, so that's the conjugate acid of water. So every acid, when it reacts, forms its conjugate base. Every base, when it reacts, forms its conjugate acid. And the other thing we'll see on a lot of acid-base reactions is this double arrow. The double arrow is telling us it's an equilibrium, that this reaction can go in either direction. So sometimes hydronium can be the acid. It can donate its hydrogen to the chloride ion, and it can form water and hydrochloric acid. Now, hydrochloric acid is a very, very strong acid. So, in fact, normally we wouldn't write this particular reaction with an equilibrium arrow because this reaction lies so far to the right. We'd make a long arrow this way and a short one going back. Something like acetic acid, now this, it's in more of an equilibrium state, so it might be more accurate to write two equal arrows, showing that the equilibrium is really somewhere in between those two. Okay, now we have a list of acids by strength and their conjugate bases. So again, we've already looked at hydrochloric acid on the top. So let's look at the ones at the top. So hydrochloric acid, notice the reason these are strong acids is because of this. They 100% ionize water, or very nearly 100% ionized water, which means when we put these in water, they form their conjugate base, and plus they give up their hydrogen ion, which again attaches to water, makes hydronium. So let's look a little bit at these conjugates as well. Notice sulfuric acid is a very strong acid. It 100% ionizes the water. But notice what it makes first. Its conjugate loses just the one hydrogen. So even though this is a diprotic acid, it has 2 hydrogens to lose, its initial reaction, its strong acid reaction, loses 1 hydrogen. Now check out our charge when this happens. We're losing a hydrogen ion, H+. So notice what happens to the charge. It becomes negative because this is a neutral compound. So if we have a neutral compound, we take away a positive charge. Not only are we taking away, again, a hydrogen, but we're also taking away a positive charge. So that is going to cause the charge on that case to go negative. Same thing with nitric acid. We're taking away a hydrogen ion. That, if we take away that hydrogen ion, we have nitrate, which is its conjugate base. Another thing we want to notice from looking at this chart, a few things. So these are strong acids. Well, they're conjugates. Because these are such strong acids, these are very weak bases. So strong acids, if we have strong acids, we have very weak conjugate bases, which makes sense. So strong acid means it's going to 100% ionize. A weak base means it's only going to maybe a tiny bit act as a base. It's a very weak power to accept a hydrogen ion. It's really not going to do it very well. So its strength as a base is negligible, as the label says there. Now, another thing we want to notice from this chart, hydronium, of course, is an acid. When it loses its hydrogen ion, it forms water, which is its conjugate base. And notice the charges on these as well. Hydronium has a positive 1 charge, so when we remove that hydrogen ion, again, we're not only removing a hydrogen, we're removing that plus charge. So it goes from being positive to being neutrally charged. Another thing, notice the conjugate base of sulfuric acid is hydrogen sulfate, right? Notice hydrogen sulfate shows up over on this side as still a relatively strong base. It's not one of our 3 that we're going to decide are very strong, but it's still a relatively strong base. Its conjugate, notice, is just the sulfate ion. It loses that extra hydrogen ion. So the first reaction of sulfuric acid is a very strong reaction. It's going to 100% ionize the water. The second reaction is still relatively strong, just not as strong. This would be more of an equilibrium reaction where it goes partially to completion, but maybe we still have some hydrogen sulfate left. So this is sometimes what confuses people, is that we can have something that's a conjugate base to one acid, and that can actually be a relatively strong acid and form yet another conjugate base. Notice some other things that are on here. Phosphoric acid, H3PO4, its conjugate, we just lose 1 hydrogen, right? And notice further down, you'll notice dihydrogen phosphate, also as well a relatively weak acid as we go down. Other thing we see as we go down this list is we're getting weaker and weaker acids. So these are strong, these are weak, these are negligible. Notice acid strength increases going this way. Notice how the base strength increases. So these were negligible. So the conjugates of strong acids were weak bases. But as we go down this chart, we get stronger and stronger bases. Notice hydroxide, what we traditionally think of as our classic base. What we saw in our first acid-base theory, the Arrhenius theory, that is a strong base. Notice other things that are strong bases that we might recognize. Ammonia is relatively getting towards the stronger end of our bases. Now, their conjugates, if this is a strong base, the methyl ion here, if that's a strong base, its acid is a relatively weak acid. So that's how our pairs work. If we have a strong base, its conjugate is a weak acid. A strong acid has a weak conjugate base. Here is an even more exhaustive list of acids and bases, well, acids and their conjugates, from a table in your book. Notice chloric acid, a very strong acid. Here's the chloric acid. Notice the chlorate ion is its conjugate base. So we have acids, their conjugate bases, acids, their conjugate bases. And we don't have to memorize what their conjugate bases are. We just have to, again, be able to remove that proton or that hydrogen ion. Now, this is a very exhaustive, well, not a completely exhaustive, but a more thorough list of acids and bases. Again, notice this has strong acids as we go up. This has strong bases as we go down, because strong acids have weak conjugate bases. Strong bases have weak conjugate acids. Now, I don't expect that you remember all of these, but we should be able to name the vast majority of them. The ones I want you to remember as being strong acids are these 3, because these 3 we're going to see so much that we have to remember that hydrochloric, sulfuric, and nitric acid are strong acids. The other thing we have to be able to do with it is we have to be able to take any acid, maybe take, say, our phosphoric acid, H3PO4, and we have to know what its conjugate pair is. So if we put phosphoric acid and water, what's going to happen? Well, we're going to form its conjugate base. So its conjugate base is this. Notice I removed a hydrogen, and I've reduced the charge because this produces a hydrogen ion. And again, anytime we write hydrogen ions, a lot of times I'll write hydrogen ions in a reaction. Really, what I'm writing, a hydrogen ion, hydrogen is always going to attach to the water. So really, hydrogen ion isn't the same thing as hydronium, H3O positive, but in water, hydrogen ions in water are hydronium. In water, hydrogen ions always form hydronium. This is really the concentration we're looking at when we talk about acids. So we need to be able to do this for any acid. We need to be able to identify the acid and the base. And anytime we have maybe a conjugate, a reaction of acids and bases, so here we have ammonium, we have perchloric acid. Anytime we have an acid-base reaction, we do need to be able to identify by looking at it what is going to be our acid and what is our base based on the reaction. So here the reaction of perchloric acid with ammonium forms ammonium plus the perchlorate ion right here. So what is our acid and what is our base? Well, this is our acid because that hydrogen ion gets donated to ammonia. So this would be my acid. Here is its conjugate base on the other side. This is a relatively strong acid, so this is a relatively weak conjugate base. Ammonia is not a strong base, but it is definitely a base. It is a base in this case because it's accepting a hydrogen ion. Here it is with its hydrogen ion, and this is its conjugate acid. So we have to be able to recognize acids and bases and label acid and base conjugate pairs. And again, the other thing we want to recognize that we talked about before is some things can be amphoteric. Right here is the word, if you're wondering how I spell it, right here in your book, amphoteric. Amphoteric means depending upon the environment that it's in, the substance can act as a base. In this case, water can act as a base, accept a hydrogen ion from sulfuric acid, or it can act as an acid. In this case, reacting with ammonia, it donates the hydrogen ion. Now it's acting as an acid. So water is amphoteric. Other things that are amphoteric, remember, hydrogen sulfate. Actually, in this case, it's its conjugate base. But if we put that in water, that could act as an acid. So this also could be amphoteric. So again, anything that we see on both sides of that list can be amphoteric. Water is really, really the big one that we need to remember. Okay, sometimes we might be wondering why some of these things are stronger than the others. Really, the main idea of why some acids are stronger than the others, it depends a lot about how polar that OH bond is. So if we have, or that hydrogen bonded to whatever it's bonded to, the bigger the difference really in polarity or an electronegativity difference, the more likely it is to lose that hydrogen ion. So here's hypochlorous acid. Hypochlorous acid, oxygen is electronegative, chlorine is electronegative. It's pulling electron density away from this hydrogen ion here. It's pulling it that way and pulling it this way. So it's pulling electron density away. The more we can pull the electron density away from the hydrogen, the more likely it is for this hydrogen to leave. So hypochlorous is an acid. Now notice chlorous, it says here, is an even stronger acid. The reason it's stronger is there's another oxygen over here. What that oxygen does is that oxygen is also pulling electronegativity away. So it's pulling it this direction and it's pulling it away over here. So it's pulling it just that little bit stronger. Pulling it that little bit stronger makes it even more likely that that hydrogen is going to leave and dissociate even more completely. Chloric acid, same thing, adding another oxygen, even more electronegativity difference, pulling electron density away from the hydrogen. And now perchloric acid, our strongest and a very strong acid, our strongest of this chlorite series, is our strongest, has the most oxygens, pulling the most electron density away from the hydrogen. So if we see hydrogen attached to something that's very electronegative or something that has a lot of electronegative pieces in the molecule, it's more likely to be a strong acid. Here's another example. We have ethanol here, which actually isn't really considered an acid. It can donate some hydrogen ions, but really doesn't in such a negligible amount. It's not really considered an acid. However, if we have acetic acid has an extra oxygen attached. That extra oxygen pulls more electron density. When it pulls more electron density, now acetic acid is considered not necessarily a strong acid, but is definitely considered an acid. More oxygen pulling more electron density away from the hydrogen, making it more likely that that hydrogen can leave and dissociate, bond into water. Now our classic example of what's going to happen when acids and bases react, we're going to look at a broader series of acid-base reactions. Our very most basic one is a reaction of strong acids with strong bases. So here we have a cup full of hydrochloric acid. Notice what we really have in solution is we have hydronium and we have chloride ions. So when we have hydrochloric acid, or really any strong acid in water, really we have hydronium ions and whatever the anion is in that substance. Now, we also have sodium hydroxide, which is a classic strong base. Again, anytime we see hydroxide, it's kind of tells us that there's strong bases in there. That has sodium hydroxide ions. When those things react, any strong acid, strong base reaction, we're going to have the chloride bond with the sodium, so we're going to form salt, and the hydronium and the hydroxide are going to react, and we're going to form water. So here we have our water and our sodium and our chlorine ions floating around. If we evaporated the water, we would just get our sodium chloride. So if we look at this reaction, let's erase everything, and let's look at what this reaction really states. If I wrote the net ionic equation of this reaction going up here, notice what it is. Chloride ions are the same on both sides. Sodium ions are the same on both sides. So really our net strong acid, strong base reaction is hydronium reacting with hydroxide to produce water. That is essentially any strong acid, strong base reaction that we have. Or maybe not any, but the majority. So we form water and we form whatever the salt is. Alright, some section review questions. It wants us to complete and balance the equations for the following acid-base reactions. I'm not going to do all of them, but let's just do some. We have H2CO3, we have carbonic acid. Carbonic acid reacting with strontium hydroxide. Well, again, this is a strong acid, this is acid-base reaction. Well, we're always going to form is water, right? So we'll form water. Now, once we form water, what else are we going to form? Well, if I remove the water, the hydrogen ions and the hydroxide ions from this, what do I have left? Strontium and carbonate. Now we do have to know the charges on these. If I look at carbonate, it's bonded to 2 hydrogen ions, so that must mean carbonate is CO3 minus 2. Notice strontium is bonded to 2 hydroxides. Hydroxides always minus 1, so strontium must be a plus 2. So my salt is going to be SrCO3. Okay, and it's balanced. That is my acid-base reaction. We'll just do one more quick and we'll be done. Sodium, hydrogen carbonate, NaHCO3, plus sulfuric acid. Well, in this instance, sulfuric acid is going to be our acid. Sodium carbonate is going to be a carbonate structure, our base. Remember what I've said before. So carbonates, if we ever see carbonates, when they react with acids, we form CO2. So we're going to form CO2. That's something we always have to watch for. So kind of a twist on our acid-base reactions. If there's carbonates, carbonates are going to bubble. They're going to form CO2. I think we talked about that last time. We still have water, and we still have what our salt left over is. Or our salt in this instance, if we take out the CO2 and we take out the water, which are the hydrogen ions, we have sodium, we have sulfate together. We have to be able to put those together, Na2SO4.